So I'm here to explain this question about phonons. So the definition of a phonon is simply just a quasi-particle that represents vibrations of a crystal lattice. So, and these are measured in units of h bar mega. So one, you can think about it as like a particle of sound. So when the crystal gets excited, you get one particle carrying h bar mega energy away in the lattice. Now, we're given this equation or this average number of phonons. So it's a function of temperature. This is just the Bose distribution. And we can just plot it. Let's use the plotting function here. Let's make the exponent just x. Let's plot it. And we can ignore the negative temperatures. So we can see the function blows up at 0, which is the high temperature limit, and it goes to 0 in the low temperatures. So let's put it here, just for reference. This is going to be our average numbers in the y-axis. And this is going to be proportional to 1 over temperature. Now, if we go to the second part, the n in the low temperature limit. So here we have 1 over temperature. So the low temperature limit is actually going to be over here. This is low T. Let's erase that. Low T. So yeah, we can see it at low temperatures it goes to 0. So there's no phonons at low temperature, which if we go to the next question, this is something we use to explain the mechanism. So thermal fluctuations cause the lattice to vibrate just randomly. So vibrations of the lattice create phonons. So as we go up in temperature, we get more and more fluctuations and more vibrations of the lattice, and we create more and more phonons. And we can see this in the graph, actually, because the high temperature limit over here, we blow up. So we just start creating more and more phonons. And since phonons are bosons, we have no limit to how many bosons we can have in the same state. So we can just make as many as we want. And yeah, that's it.